In the 17th lecture, we will discuss some common methods to deal with the assumption violations in the linear regression models. Transformations can help the model fit and correct violations of model assumptions. We may transform data to improve model linearity, variance homogeneity, and error normality. Transforming the response is more common than transforming the predictors, since transforming predictors is only appropriate for nonlinear issues. Using transformations can be an iterative process, since assumptions appear to hold prior to transformation may no longer hold once a transformation is applied. Finally, transforming data, especially the response, can make the model harder to interpret. The table below shows some common transformations: natural log transformation, square root transformation, inverse transformation, and Box-Cox transformation. The right column shows the simple regression model after the transformations. The Box-Cox transformation transforms the response from y to gy for positive y. We may choose lambda using the maximum likelihood, where RSS lambda is the residual sum of squares using gy as the response. It is a popular method to transform non-normal data into a more symmetric, close to normal shape. The linear regression may be generalized to model nonlinear relationship between y and x. A useful method to describe nonlinear relationship is to add polynomial terms. The general form in the simple regression is this, where D is the polynomial order. In practice, we may use orthogonal polynomials instead of the natural polynomials to avoid multicollinearity. In R, the function poly constructs orthogonal polynomials. The example below models an underlying exponential relationship y equal to exponential of x plus a normally distributed noise. Three regression results for D of 1, 2, 3 are shown here. When the model includes only linear term, the adjusted R-square is 0.856, and the term is highly significant. When the model includes both the linear and the quadratic terms, the adjusted R-squared increased to 0.873, and the quadratic term is also significant. When the model further adds the cubic term, the adjusted R-square is still 0.873, and the cubic term is not significant. Thus, we have the optimal fit of D equals to 2, which suggests that the inclusion of the quadratic term in the model is appropriate. In addition to polynomials, we may use splines to include local influence as an alternative to model a nonlinear relationship using the linear regression. When errors are dependent, there is a certain degree of correlation between the errors. We can use generalized least squares in the linear regression. If we know the variance-covariance matrix, then we may reduce generalized least squares to ordinary least squares and estimate the regression parameters using matrix transformation. If the covariance structure is unknown, we may try several common structures and choose the one that provides the best fit. The following table shows some common covariance structures. For example, compound symmetry is the simplest covariance structure that has within subject correlated areas. The correlations are the same, regardless of how distant in time the repeated measures are. First-order autoregressive AR1 systematically decreases correlation with increasing separation between time points as rho to the power of time difference. ARMA11 is the first-order autoregressive moving average model with off-diagonal term gamma rho to the power of time difference minus 1. The top structure is similar to AR1 in that all measures are at the same time have the same correlation. So AR1 is a special case of top. The most generalized structure is the unstructured that allow every term to be different. In R, the GLS function in the NLME package may be used to fit a generalized least square model. Sometimes the errors are uncorrelated, but they have non-constant variance. Thus, the homoscedasticity assumption is violated. As discussed previously, we may use a transformation to improve the variance homogeneity. We may also use the weighted least squares to improve the homoscedasticity when the form of the variance is known. The method is a special case of generalized least squares. The covariance matrix is diagonal, where Wi are the weights. The simple regression can be transformed to this, and weight may be assigned as the inverse of its variance, so that the variance of the transformed error is a constant. For example, if the error variance is proportional to x, then we may set the weight as the inverse of x. If the form of the variance is unknown, then we may regress the residuals on x and use the inverse squared fitted values as the estimated weights. In practice, the weighted least squares method may also be used to correct the sampling bias to ensure the sample is a good representation of the population. When the errors are normally distributed, ordinary least squares is the best method. When the errors deviate from the normal distribution, we may transform the outcome into a shape closer to normal. However, we may still have long-tailed error distribution or more than a few outliers. The ordinary least squares method is extremely sensitive to outliers. Robust regression methods provide an alternative to least squares when the data does not follow normal distribution or have more than a few outliers. One robust regression method is M-estimation, which could be related to weighted least squares. Instead of minimizing the residual sum of squares RSS directly, we minimize the sum of a function of the residual. This function is called the objective function rho, and the function is related to the weighted least squares since the corresponding weight is the derivative of rho divided by the residuals. The table here lists the function in the least squared method, the least absolute deviation method, and the Hubbard's method. In the least squares, the projective function rho is the residual squares, and the weight function is a constant. No use in the estimating equations. The method minimizes the residual sum of square RSS. In the least absolute deviation method, rho is the absolute of the residual, and the weight function is its inverse. The Hubbard's method is a compromise between least squares and the least absolute deviation. Here, C is a constant could be estimate of sigma. The method is least squares when the absolute residual is less than or equal to C, and the least absolute deviation when the absolute residual is larger than C. In R, we may use function RLM. In math package to use the Hubbard's method. Another robust regression method is the least trimmed squares method. It minimizes the sum of squares of the Q smallest residuals. In R, we may use function LTSREG in robust base package. The default Q is n over 2 plus p plus 1 over 2. The least trimmed squares method may capture the trend in the main group of data, while the M estimation may not. When we have a multiple linear regression model, we need to be aware of the multicollinearity among the independent variables. When they are related to each other, we may have the multicollinearity issue. Collinearity makes the model unstable and saps the model's statistical power. For example, if we regress the student final exam score on the midterm score and the time student spent on the course, we may have high collinearity since the midterm score and the time spent on the course are related. The multicollinearity may be estimated by the variance inflation factor VIF. VIF is the inverse of 1 minus r squared j, where r squared j is the coefficient of determination when we regress xj on all the other predictors. Normally, a VIF of 10 and above is an indication of high multicollinearity. We may suggest using a lower VIF threshold in practice. Sometimes multicollinearity may change the significance and even the sign from the simple regression with the predictor xj alone. For example, if beta j in the multiple linear regression and alpha j in the simple linear regression have different signs, then it is possible that xj is related to other predictors in the multiple regression model. This is an example with 20 participants in a psychology test. We have one overall test and 5 component test scores. We would like to know if there is any association between the overall test score and the component scores. In SAS, the option VIF in the reg procedure here calculates the VIF for each predictor. The model has a large R squared exceeding 0.9, an indication of a strong model. The VIF values from the table suggest that X1 has the highest multicollinearity. The VIF indicates the overall correlation. In order to be more specific, we may need to study the Pearson correlation coefficients among the independent variables. The table below shows the correlations among the 5-component test scores. The sample size is 20 and the null hypothesis is rho is 0. We may reject the null if the p-value is less than 0.05. For example, the table shows that x1 is strongly correlated with x2. Rho is 0.87 with the p-value less than 0.0001. Also, x1 is moderately correlated with x4, and rho is 0.65. In addition, x4 is weakly correlated with x2 and x5, both significant at 5% level. Multicollinearity is a complex issue to deal with. We may need to use one or more techniques to reduce its impact, depending on different situations. We may remove high correlated predictors based on their impacts on the models. We should remove predictors one by one, since any variable removal may affect the estimates and the significance. We should remove the least significant predictor first. In the last example, x3 and x5 should be removed first since they do not offer significant enough contribution to the model. Then we should remove the predictors with high VIF. Although x1 has highest VIF, we should remove x4 instead, since it is the least significant predictor. After x4 is removed, x2 is the least significant and should also be removed. Thus, it becomes a simple linear regression model with only one predictor, x1. The model still has a R-squared of 0.9, suggesting that the first component test score represents 90% of the overall test score. The t-value of x1 is 12.6, which is highly significant. Transformation may also be used to reduce the multicollinearity. For example, we have a regression model with predictors x and x squared. Since x and x squared are related, we may instead transform them to orthogonal polynomials. Sometimes we need to standardize the predictors to reduce the multicollinearity. The standardization is a technique useful in statistics and machine learning. We may also derive new predictors to replace the correlated ones. For example, if the predictors are repeated measurements, then differencing could be used as in time series. Also, we may use different analysis methods such as partial least square regression or principal component analysis. In summary, we learned how to deal with the assumption violations in the linear regression models. We may transform data to improve model linearity, variance, homogeneity, and error normality. Transforming the response is more common than transforming the predictors, since transforming predictors is only appropriate for non-linearity. Some common transformations are natural log transformation, square root transformation, inverse transformation, and the Box-Cox transformation. One method to describe nonlinear relationship in the linear regression model is to add polynomial terms. In practice, we may use orthogonal polynomials to avoid multicollinearity. When the errors are correlated, we can use generalized least squares if we know the variance covariance matrix. If the matrix is unknown, we may try several common structures such as compound symmetry, autoregressive model, autoregressive moving average model, and even unstructured model. Then find the best fit. If the errors have non-constant variance, we may use the weighted least square to improve the homoscedasticity. The method may also be used to correct the sampling bias to ensure the sample is a good representation of the population. When the errors deviate from the normal distribution, we may use robust regression methods such as M estimation and the least trimmed squares model. The Huber's method, one estimation method, is a compromise between least squares and the least absolute deviation. The least trimmed squares method minimizes the sum of squares of the q smallest residuals. We need to be aware of the multicollinearity among the independent variables in a multiple linear regression model. The multicollinearity may be estimated by the variance inflation factor VIF. Normally, a VIF of 10 and above is an indication of high multicollinearity. To deal with high multicollinearity, we may need to remove highly correlated predictors, transform the predictors, standardize the predictors, derive new predictors, or use some different analysis method, such as partial least squares regression or principal component analysis.